Okay, welcome everybody. Let me just hit this button here. Okay, good. In the last few lectures, we've been looking at the geometry of solutions of linear ODEs, right? And we're just starting to think about nonlinear ordinary differential equations, which are much more like what we're actually going to come in contact with on a daily kind of research basis. And so what I'm going to do today is just briefly review kind of all of the canonical types of solutions you can get for a linear system. And then we're going to dive into nonlinear systems that come from potential energy equations. Okay, so we're going to get into some physics today, some nonlinear ODEs, and we're going to see how this geometric view of ordinary differential equations makes sense with physical systems. I posted the third homework today. It is due next Friday, and the week after homework 3 is due, there will be a midterm exam. So the midterm will come out on Wednesday, and I think it'll be due on Friday, which is Halloween, but it'll be due way before everyone should start drinking, hopefully. There could be some overlap. And I think that there's no homework due on the Halloween week. There's a homework due the following week. Okay? So I'm just going to do a quick overview of 2 by 2 linear systems, x dot equals ax. So I'm just going to go down the list, and we're just going to draw pictures so we have them kind of in the back of our mind, okay? So if my A matrix is something like 1, 0, 0, 2, what does that solution look like? It's unstable. How do you know it's unstable? Positive eigenvalues. What are the eigenvalues? 1 and 2. You can always read them off for a diagonal or an upper or lower triangular matrix. Okay? So the eigenvalues are 1 and 2. What are the eigenvectors? This is a diagonal matrix. So the eigenvectors are the unit x direction and the unit y direction. Okay? So it's a little more unstable in the y direction, but it's still pretty unstable in the x direction. And so my solutions look like that. Every single solution you can think of, except for ones that stay exactly at the origin, will explode away from the origin. Okay, this is called an unstable source. Okay, let's try another one. A equals 1 minus 1. What's that, stability-wise? Okay, it's called a stable. It's called a saddle. Is it stable or unstable? Not both. It's unstable. It has one stable direction, but the other unstable direction will pretty much always take me away from the fixed point. Again, what are the eigenvectors? What's the unstable eigenvector? The x-axis. What's the stable eigenvector? The y-axis, right? The one corresponding to this eigenvalue. So the y-axis is stable, the x-axis is unstable, and pretty much all of my solutions still move away to infinity, but they move away to infinity on the x-axis, on this manifold. Okay, this is called a saddle. And it's definitely unstable. Okay, what if I have A equals 0, 1, minus 1, 0? What about that one? Sorry, you say stable or unstable? Unstable. Why do you think it's unstable? What are the eigenvalues for this one? Okay, so this one has eigenvalues plus or minus I, and so it's going to be oscillatory. We're going to get pure sines and cosines. Let's not think about the eigenvectors for now, but basically the whole plane, both the x and the y directions, are stable. And so I get these closed orbits, where if I start with a given radius, I keep that radius forever. Okay, this is kind of stable. We call it stable, but it's really neutrally stable. So solutions neither grow nor decay. They just kind of stay at the same size. If I added a little bit of nonlinearity to this equation, then this could go either way. It could become stable or it could become unstable. Okay, let's say I do one final one. I have A equals minus 1, 1, minus 1, 0, minus 1. What about this one? This is the last one we did in class, yes, on Wednesday. Okay, well, these eigenvalues aren't too bad. It's lambda equals -1 plus or minus I. And so is this stable or unstable? How many think it's stable? How many think it's unstable? How many think it's neutrally stable? Okay, so this is stable. The way we know is because it has real part. If the real part of lambda is negative, then it's stable. If the real part of all of my eigenvalues are negative, then my system's stable. Okay, because my solution's going to look like e to the lambda t. It's going to look like a bunch of e to the lambda t's. And that's going to be e to the -1 plus or minus I -1 plus or minus it. And remember, exponentials, if I multiply two exponentials, the exponential sums. So this is e to the minus t times e to the plus or minus it. Okay, this is just sines and cosines. And this is a pure decay. Okay, so I have a magnitude of my solution decaying, and the solution's oscillating while it decays. So remember, the solution to this looked like, I have this exponentially decaying envelope, and my solution is oscillating as it decays. So the phase portrait here is x1, x2 kind of spirals into the origin forever. Okay, so it's stable. And this is called a stable spiral because it's spiraling in. How would I make this unstable? Yeah, I could make this real part +1 by changing these diagonal elements to +1, and then this would be an unstable spiral, and it would blow up and oscillate as it does it. Okay, that's pretty much it. The other, of course, for this unstable source, I could also have a stable source if I just made my eigenvalues negative. But these are the basic building blocks for all linear systems. Okay, in higher dimensions, you still have these basic prototypes. You have things that are purely stable or unstable. You have things that are a mix of stable directions and unstable directions, still called saddles. You have things that are still neutrally stable, all purely imaginary complex pairs. And then you have combinations of, damped or undamped oscillating complex pairs. There's one last type of system that I haven't told you about, and that's where I have eigenvalues that are really, really close to each other. Here, I'll just write it out over here. It's where I have eigenvalues that are really close to each other, like -0.010, -0.011. But I have eigenvectors that are very, very close to parallel. Okay, so if I have eigenvectors that are super close to parallel and eigenvalues that are really close to equal, I get interesting phenomenon. So this is still a stable system, but it has really interesting transient dynamics. So this is a homework problem on homework 3. I want you to play around with this, and we'll talk about it more probably on Monday. But we haven't talked about this system yet. It's a little interesting. Okay, any questions about these before we go on to looking at physics? Yeah.
So maybe I can't recall, but the other terms that are not on the diagonal, -1 and the 1.
Yeah.
Are those physically damping terms?
No, so the diagonal -1 terms are the damping terms. So if you compute the eigenvalues of this, you'll find that the negative part comes from these diagonal -1s, and the oscillatory part comes from the off-diagonal, equal and opposite plus and -1 terms.
So is there a physical coordinate to the oscillatory terms that we should think about?
So when we dealt with the spring mass system, we had a slightly different form of the equations, but we also got purely complex eigenvalues. So what I would recommend doing is take that spring mass system and add a damping term and see how it changes the A matrix. And you'll really see which terms contribute to damping and which terms contribute to pure oscillation. But the oscillatory term really corresponds to the position and the velocity being out of phase with each other. Okay. Okay, good. So this is, usually I'm used to teaching applied math classes, and I always promise my students that I will never have any physics. They don't have to know any physics at all, but fortunately I assume that most of you know a lot of physics, possibly more physics than I know. So how many of you have seen Euler Lagrange equations or Hamiltonian equations sometime in the past? How many have not ever seen it? Okay, it's fine. We're only going to kind of use them as examples of equations. But before jumping into Lagrangians and Hamiltonians, I want us to think about just a particle and a potential well. My old professor used to love potential fields, and he would always take us through journeys of pot fields, which is a lot of fun. Okay, and we're going to use this as an example of linearizing nonlinear ODEs. Okay, good. So when I say a particle and a potential well, it really is pretty simple what I'm talking about. So I literally mean I have some potential V, capital V of x, of some variable x. Maybe there's some potential shape, some potential function of x. And you can literally think of this as like, if I drop a ball bearing on this surface, what does the ball bearing do? All right, if I drop it here, it just oscillates back and forth until I add damping, and then it oscillates and dies. If I drop it here, it'll move. Let's say it's a bead, so it's constrained to stay on this path. Then it'll move very quickly up to the same height over here, and then it'll move back, and then it'll keep going and going and going until I add damping, in which case it'll get trapped in one of these wells. What if I put it directly on the top of this hump here? It'll stay there unless you breathe on it. Okay? So really simple. I literally mean there's a bead on a wire, and that wire has a shape V of x. Okay? So consider a potential V of x, and imagine sliding a bead. On this surface. So this might seem a little cutesy, like a toy problem, but this is really the first step in a huge range of like all of classical mechanics. Okay, so almost any problem in classical mechanics, a pendulum, a double pendulum, an automobile, the planetary motion, you start with the potential field. Later we'll add the kinetic energy, and we'll get the equations of motion. Okay, so this is going to be an extremely general mathematical construct, but for now let's just think of a bead on a wire. Okay, so how many of you remember what the force is for a particle in a potential field? The F equals ma force. These are conservative forces because I haven't added any friction. Sorry? Well, so in general, the force is F equals minus partial V partial x. Okay, so I have like more force when I have a bigger slope, less force when I have a smaller slope. Okay, so for example, at this hump here and at these troughs here, I have zero slope with respect to x, and I have no force pushing me in the x direction. Okay, my bead doesn't move. If you want to think about the gravitational potential is like 1 over x. And so the partial of that with respect to x is 1 over x squared, which is our force that we're used to, right? That's the gravitational force, 1 over x squared. Okay, so this is from physics. And so what we end up getting is essentially x double dot equals minus partial v partial x. So I'm assuming that my mass is equal to 1. Okay, I have a unit mass bead. So this is nice. I have a differential equation. This looks a lot like differential equations that we are pretty comfortable with solving now, right? So we have a second order system. We can write it as two first order coupled systems, and then we can find the fixed points, find the linearization, solve the system. Okay, we know how to basically solve this. So we're going to do two examples of this potential well problem today. I can't help it. I'm going to write down the Lagrangian. I really, really, really like the Lagrangian. This is probably the most important. So physicists have been talking about a grand unified theory of physics for all of my life, and they're massively overlooking the Euler Lagrange equations. This is the closest thing we have to a grand unified theory. It covers special relativity, general relativity, classical mechanics, and quantum mechanics. All of them in one equation. Okay? Simultaneously if you write the coordinates correctly. Okay, so let's write the Lagrangian. Lagrange was awesome. So they had a library at Caltech, a math library, and it was a pretty big library on the 7th floor of the big tall building on campus. And Lagrange had 2 full bookcases with like 7 shelves just for his combined volumes of math and physics. He's one of the most prolific mathematicians and physicists to ever live, and he really got a tremendous amount of stuff right that we're still digging through his works, finding new inspiration today, which is amazing. Okay, so kinetic energy is, what's the kinetic energy of a particle with position x and velocity x dot? Yeah, 1/2 x dot squared. I'm just going to make all of my masses equal to 1. I get to do that because this is a math class. So my potential energy is v of x, and the Lagrangian is going to be so L of x and x dot is equal to my kinetic energy, usually just a function of x dot. Not always. Sometimes it can depend on x. That's weird, but it happens. Minus my potential energy, which is usually just a function of x, the position. Okay, for those of you who can't see it, it's on the side screen too. Okay, and so we can write down the Euler Lagrange equations. As the time derivative ddt of partial L partial x dot minus partial L partial x equals 0 for an unforced system. If I have external forcing, then there would be some generalized force or torque on this right-hand side. Okay? I mean, so I'm not deriving this. I'm just showing you what it is. These are the Euler Lagrange equations if I write my Lagrangian as kinetic minus potential energy. This is the equation you get when you write down the principle of least action. What this means is that this particle on this wire is going to try to find the most efficient path that minimizes the transfer of potential to kinetic energy and vice versa. So the principle of least action, right? That's why light changes direction when it goes through different media. Like if you have light going from air into water, it turns. It's because of the principle of least action. Balls rolling down a hill, the trajectory they take is because of the principle of least action. Quantum mechanics and relativity also satisfy the principle of least action. This is just the ODE form of the principle of least action. And you have to take my word for it. You know, this isn't a physics class. I'm just writing it down. Okay. So what you can do is you can actually plug in this kinetic energy and this potential energy. And you'll find that partial L partial x dot is the same as partial T partial x dot, which is just x dot. And ddt of that adds another dot. So I have x double dot equals partial L partial x. But the only part of my Lagrangian that depends on x is my potential. So this equals minus partial v partial x. Okay, so this is just another way of getting this equation from the Euler Lagrange equations. Okay? What's nice about this, you could derive this this expression using Newton's second law, F equals ma, in a Cartesian coordinate system. But the Euler Lagrange equations work in generic coordinate systems. So they work in the pendula using angular coordinates, and I don't have to do any nasty cosine and sine transforms to polar coordinates. It just works. If I can write down my kinetic energy and my potential energy in that coordinate system, I can get equations of motion. Really, really nice. Okay, good. That's probably enough physics. Any questions about these equations before I go on? Any at all? We're going to start using them. Yeah? Okay. Let's do an example. This is one of my two favorite vector fields. I have favorite vector fields. This is my second favorite vector field. Okay, so x double dot equals minus x plus x squared. And this corresponds to a potential energy of... How would I figure out what the potential energy is for this ODE? Yeah, I would take minus the integral, because I know that this is equal to minus partial v partial x. So I'm just going to integrate it and take the negative sign, and I get something like x squared over 2 minus x cubed over 3. Good. And I can plot that potential curve, and it looks something like this. So I'm going to use capital V with these little bars on top to denote the potential energy, and I'm going to use little script v to denote the velocity, because this thing has a velocity. Okay. That's what the potential energy looks like that gives me this ODE. Okay, so physically, we should know exactly what's going to happen for every case I can think of. Right? I'm dropping a bead on this. We can all picture in our minds. We all have integrators in our minds that we learned. So we learned how to integrate this system physically in our minds, and we know exactly what the bead's going to do. Okay, so let's say I have the bead right near this top of the potential energy hump, and I kick it a little bit to the right. What's going to happen? It's going to go down forever. If I kick it a little to the left, it's going to oscillate and then come right back, and then oscillate and then come right back, unless I have friction, in which case it's going to get trapped in this well. Okay? Now, what's interesting is we can also think about not just starting this at initial positions, but also giving them some initial velocities. So let's say even if I start below this hump here, but I push it to the right, I give it a kick to the right, it might still make it over the hump and go to positive infinity. So physically, we know exactly what the system is going to do. That's why I like these, because we know exactly what the system is going to do. And so the ODE actually makes physical sense when we write it down. OK, so how do we solve ODEs like this? What's the first step? So I would probably try to linearize it, but I would start by writing this in a suspended, I'd add a variable for velocity, right, to make this a first order system. So I have x dot equals some little velocity, and my velocity dot is minus x plus x squared. It's fine. So what are my fixed points? What are my fixed points where this is equal to 0? Okay, so x is equal to 0 and 1. What about v? 0. And again, that makes sense, right? That corresponds to x being at 0 or x being at 1 with 0 velocity. Those are my two fixed points where the bead stays still. Okay, and I can write that as 0, 0, the vector, and 1, 0, the vector. Okay, those are my fixed points. Now what do I do? What's the next step? I have fixed points. I have a system of two coupled first-order nonlinear differential equations. I linearize this nonlinear system about each of these fixed points. And I look at what those eigenvalues and eigenvectors of that linearization are. Okay, so this function f, so d f d x and v is equal to partial of this with respect to x is 0, partial with respect to v is 1, partial of this with respect to x is minus 1 plus 2x, partial of this with respect to v is 0. Okay, so fixed point 1 is 0, 0. It's this point right here. So df dx at 0, 0. So I plug in 0 for x and v in this expression. What do I get? Perfect. Okay, this is one of the canonical cases we wrote down earlier, right? This has purely imaginary eigenvalues. It's a center, so my solutions just oscillate at the same radius forever. Okay, so this is a center, and it looks like that. Okay. So for fixed point 2, again, I take my linearization df dx, and now I plug in the vector 1, 0 for x and v. And what do I get now? So I plug in 1 for x here. 0, 1, 1, 0. Okay? And I'm pretty sure that this gives me eigenvalues that are both positive 1. That's not good. So it's very unstable. And yeah, okay. Sorry, I think this gives me eigenvalues that are plus and minus 1. Right? So this is lambda equals plus and minus 1, which makes this an unstable saddle. Okay, so that means I have a stable direction and an unstable direction. If I wanted to know what those directions were, I would have to compute the eigenvectors. Okay? Okay, good. Any questions so far? We have a particle on this potential surface. We wrote down the equations using f equals ma. We've linearized about our two fixed points, and we find out that one of them is stable and one of them is unstable. It's a saddle. Okay. So now we're going to draw the complete full phase portrait of this problem and see if it makes physical sense. Okay. And this thing actually has eigenvectors. So you can verify this in MATLAB that this has eigenvectors 1, 1 and 1, minus 1. So my saddle is actually rotated by 45 degrees. So it's actually stable here, unstable here. Okay, remember, we look at the eigenvalues to figure out its stability. Then we look at the eigenvectors to figure out which directions the stable and the unstable directions are. Okay, so you can just verify that for this matrix, these are the eigenvectors, and this is what my saddle looks like. It's rotated by 45 degrees. Okay, so now we're ready to draw the phase portrait. And we're going to draw position versus velocity. Okay, we want to know what the position does with respect to the velocity and vice versa in time for this problem. So I have 0, 0, and I have 1, 0. Those are my special points that are fixed points. So what do I know is true in a small neighborhood around 0, 0, the fixed point 0, 0? It's a stable center, right? Okay, so I can draw that as, I'm going to use blue for neutrally stable. I think that is about right. Okay, so around a small vicinity of this fixed point, I'm going to have kind of neutrally stable solutions. Okay? If I start in, just to have our picture here, if I start in a vicinity of this well, I'm just going to oscillate around that well forever. That's what this is showing me, that my position and velocity are just oscillating out of phase in circles. Okay? What about in a small vicinity of this point 1, 0, which corresponds to me being at the top of this hump with no velocity? It's a saddle. It's unstable, and it's rotated by 45 degrees. Okay, so locally, I'm going to have an unstable direction, and I'm also going to have a stable direction. So green is moving in, red is moving out. And I would have been able to tell which of these was stable and unstable by looking at the eigenvectors. Which eigenvector corresponded to lambda plus 1, and which eigenvalue corresponded to lambda minus 1. So which of these eigenvectors corresponds to lambda minus 1? The green, because it's stable. Okay? And then we can start piecing together what happens in the middle, just using our physical intuition. Okay? So for example, if I'm on this point and I nudge it ever so slightly, either left or give it a negative velocity, it's going to move down to the same potential height, and then it's going to turn around and come back up and ever so slowly reach the top again. Right? That's one of these solutions. That corresponds to pushing either a little to the left or a little down. We follow this red curve until we come back to that fixed point in infinite time. This takes infinite time to go around this trajectory. Okay? What if I push it a little harder? What if I'm at this top and I push it to the left, a negative velocity, pretty hard? Well, it's going to overshoot, and then it's going to go over the hump and down to positive infinity with positive velocity. Okay? So that corresponds to here, right? I have a large negative velocity at that x position. At this x position, I have a large negative velocity. So I'm going to overshoot, come back around, and then go to infinity. In x, I'm going to go to x infinity with positive x velocity. And that's going to accelerate and accelerate and accelerate. So we actually know what's going to happen basically for all time. The final case here, I can just draw this for you. If I start out here, like way out here, then I'm just going to go to positive infinity. Okay, so this is the phase portrait for this problem. This is what, essentially, like this is the solution of the ODE. This is one form of the solution of the ODE. Lots of times, we can't write down x of t equals blah, 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 blah. Right? For nonlinear systems, I can't actually write down a closed form solution for you for lots of problems. But I can draw you the picture that tells you everything that's going to happen in the system. For every single initial condition you can name, I can tell you where that initial condition will go. Okay, so this is called a phase portrait because it tells you the phase between the variables. And we obtain this by finding fixed points and their linearizations. And then for this problem, we just used our reasoning to figure out how to connect the two. Okay, questions? This is kind of probably new for some of you. Yeah?
The center, is there any particular reason that the arrows are
That's a good question. There is a reason why the arrows are pointing clockwise, and I think, I don't know, I might mess this up, but I'm pretty sure that it's the difference between this and this. So if the negative is switched, I think it switches the order of the circle, but I'm not 100% sure about that. Yeah. There's a slim chance, I could have bombed the direction of these arrows. You should double check on your own. Okay, it's actually, it's worth really looking at what the eigenvectors and eigenvalues are. And usually I can tell what direction the center has to go by looking at the direction of my saddle, because I know that it has to go this way if my saddle's coming in and coming out this way. Okay, other questions? So this may seem like we took a simple system that we actually understood and we made it really, really complicated. That is kind of what we just did. But what's nice about this picture is that this is a geometric way of thinking that generalizes to much, much harder problems than just a bead on a wire. Okay, this is exactly how we design spacecraft trajectories to go to orbit the moons of Jupiter. Okay? In fact, this looks eerily like the phase portrait for the Sun-Jupiter system, except that one has an extra dimension. So there's a direction coming out of the plane that makes this a bulb, and this is rank 1 saddle. So it's got 2 stable directions and 1 unstable direction. Okay? So this picture allows us to visualize systems and solutions that we can't write down closed form solutions for. Okay, other questions? I'm going to expect you to know how to draw phase portraits. So if you have questions, I want you to ask them. Okay, we find our fixed points. We linearize around those fixed points to find out what the geometry looks like. And at the very least, we could draw a picture in this vicinity and this vicinity. But sometimes with good physical intuition, we can actually draw the full global phase portrait. Yep.
So it will take infinite time to complete the trajectory and come back.
Mm-hmm.
You get that information from the...
This is just from physics. So let's say I perturb a teeny tiny epsilon in this red direction, which corresponds, imagine I had a bead sitting here and I push it like 1,000th of a millimeter over and there's no friction. It's going to take a really long time to accelerate down, and then it's going to take a really long time to come back to rest at the top. Okay? Okay, I'm going to do another example, and then if I have time, I'm actually going to show you what the geometry of this looks like for the Sun-Jupiter problem, because it's awesome. If I can find it. So for example, on homework 3, you're going to draw this phase portrait for the pendulum system. Okay, you have theta double dot equals minus sine of theta. You're going to draw the phase portrait for that system, with and without damping. So let's add damping here. Okay, let's say I add friction to this system. Simple enough. I wish I didn't erase my board. X double dot equals, was it plus or minus x? Minus x plus x squared? Minus x dot. We're going to add damping. Now, we're not going to go through and recompute all the eigenvalues. It's a pain in the ass. But let's just guess what the solution is, because we know physics. Okay, this point was a center, and this point was a saddle. What do you think happens to the center when I add damping? It becomes a stable sink, a stable spiral, right? So if I start here, now I oscillate, but I don't get to quite the same height. Then I oscillate again, and I oscillate again until I eventually have no energy, and I rest in that well. So it's a stable spiral sink. Okay, this is one of the cases we wrote up on the board in the first part of the class. The saddle is much more robust to small changes in the linearization. It's still a saddle. This saddle is going to stay the same. So now what I have, this is kind of a fun picture to draw. See if I can do it. So now the origin is a stable spiral. And I still have my saddle point out here. Is that right? Yep. Except now, this trajectory gets, instead of coming around and coming back to rest at the fixed point, it gets trapped in the well. So if I take this point and I nudge it a teeny little bit to the left now it's going to oscillate, but it's not going to get quite as high because there's friction. And now it's not going to get quite as high, and it's going to come to rest in that stable fixed point, which is exactly what this picture is showing, that I'm coming to rest in this fixed point. Then some other trajectory has just enough energy to come to rest at the top, and then everything else just goes to infinity, like we expected. So the only difference here is that this center, instead of having closed circular orbits, it now becomes a spiral sink. So when I add damping, my center here became a spiral sink. You could have figured this out by looking at the eigenvalues of the linearization. You would have found that these eigenvalues are now stable. Or you could just think about it physically, like if I add damping, this well becomes an attractor. It stabilizes. Questions? Should make some physical sense, right? Like this picture now, this idea of a spiral sink should really kind of make sense. It's this well with friction. Okay, for the last example, this one's kind of neat. This is my first favorite vector field, in 2D at least. I guess my favorite vector field in 3D is the three-body problem. Okay, so this one's really cool. So now we're going to have x double dot equals minus x cubed plus x, and then we'll have this optional damping. Okay, and this corresponds to a particle in this potential field where we have a double potential well. It's not a lot more complicated, right? This is, if I integrate this, I get an x to the 4th over 4 minus an x squared over 2. And that's exactly what this potential well is. And again, the bead, it's going to stay in this well if it starts with low enough energy. It's going to stay in this well if it starts with low enough energy. If it starts up here, if you kick it to the right, it's going to go around and around. We know what this solution is going to do. So we write this x dot equals, call it y dot equals x minus x cubed, and then again, my damping term is this optional minus y. Okay, so what are the fixed points? Let's say, forget the damping for now. What are the fixed points of this system? Okay, so y definitely has to equal 0, yeah? And x could be 0 or plus or minus 1. Okay, so this is minus 1, plus 1, and 0. These are where my partial derivative of u with respect to x equals 0. Okay, so I can compute the Jacobian of this, or my linearization. So d fd vector x is equal to 0, 1, and then 1 minus 3x squared, 0. If I had damping, there would be a minus 1 here, right? Because there would be a minus y here. So maybe I'll do that in blue. So there could be a minus y here for optional damping, and then I would get a minus 1 here, and it would make my eigenvalues stable in the wells. Okay, now you can kind of, in MATLAB, now you can just plug in these fixed points into this equation, and you can get the eigenvalues and eigenvectors. And what we're going to find is that our fixed points are, 0, 0, 1, 0, and minus 1, 0. And when I plug these in and compute the eigenvalues and eigenvectors, I find that the 0, 0 point is a saddle, and that both of these points are centers. They have kind of plus or minus I eigenvalues. And this is kind of like plus or minus 1. Makes sense. This point is a saddle, and these points are centers. Like, we should just be able to write down the phase portrait for this. I don't even need to do the linearization or the fixed points. I know exactly what the system's going to do. So let's just do that. So now in the x, y variable, so y is my velocity here, we have 3 fixed points. We have one at -1, 0, and +1. Okay. I know that both of these wells with no damping are centers. Okay, so I can have circles here. I think they're going this way. Can't guarantee it. Let's go with it. Okay, and then I have a saddle point here with an unstable direction. And again, I would find out what direction this is by looking at the eigenvectors of the linearization at that point. And a stable direction. And the orbit that couples these two is very, very similar to before. Okay, so if I start in this well, I stay in this well. I just oscillate back and forth. If I start in this well, I stay in this well. I oscillate back and forth. If I kick this saddle a teeny bit to the right, I go around to the right, and then I come back. And the same thing for the left. But if I give a little more energy, let's say I start it with a pretty big kick in this direction, then I'm going to move up higher than I was before, come back around, and then go up higher than before and come back around. And I'm going to, so that's this x position, but with a little more velocity. I go around and around and around forever. I just keep going around and around and around forever. I go up and then back, and then up and then back, forever and ever and ever. So that's the phase portrait for this system. I mean, you should be able to do this for the pendulum now, right? We have saddles and centers. We know exactly what it's going to do. Yeah?
Do all the lines on the phase portrait always have to have arrows? Because in that example, it seems like that oscillation would work in both directions.
Every line has to have an arrow. The arrow tells me which direction time is going. Time goes forward. This direction goes this way in time. And it really is this way instead of the other way, because if I think about it, if I start with a positive velocity at this position, that's a positive velocity, then my x moves in the positive direction. So it has to go this way. If I start with a negative velocity, if I push it this way, so now it's coming back around and it's got a negative velocity at that point, my x is moving in the negative direction. So this arrow really has to point this way. Okay, there's all these little tricks to check which way your arrows are pointing correctly. Okay, I will let you figure out what this looks like if I add damping. It's awesome. These break into spirals. I have a t-shirt that I made that has this vector field with spiral sinks, and I'll show you sometime. But I want to show you this in PPlane, a MATLAB function, because this is really, really useful. And I have 2 minutes left, so I'll do it quickly. Perfect. Okay, you can go to Google, you can type in PPlane, and then you can download this function from a website at Rice. It's called PPlane. It's awesome. You hit F5, and we're going to run it. And then I type in my vector field. So my vector field is x dot equals y dot equals x minus x cubed, and I am going to add friction, minus y. And I'm going to plot from like -5 to 5, -4 to 4, something like that. You click Proceed, and it will draw all of these arrows. And I can click anywhere in the screen I want, and it'll draw the phase portrait for me. It's awesome. I'm just going to keep clicking because this is a lot of fun. And so you see that I have a saddle point in the middle, and it's kind of mediating where trajectories, which well the trajectories get trapped in. Some of them get trapped in this left well, some of them get trapped in this right well, and everything from infinity is getting sucked into one of these two wells, right? Because every trajectory on that curve will eventually get damped out to be living one of those two wells. So you can use PPlane on the homework. This is fine. This is a great tool. You could write your own PPlane using ODE45. It's not that hard. This is a pretty slick program, though. OK, that's everything today. Thank you.